In this session, we're going to see how to find upper and lower bounds on zeros, in particular zeros of polynomials. Okay, well, we're really going to see how to recognize upper and lower bounds. First, let's describe them. An upper bound is a positive number such that no solution to a polynomial is bigger than it. So on a number line, no solutions are to the right of an upper bound. A lower bound is analogous. It's a negative number such that no solution is smaller than it. In other words, on a number line, there are no solutions to the left of a lower bound. So all the zeros of a polynomial are contained in an interval that is defined by the lower bound and the upper bound. Let's see how we would recognize these bounds. Here we're asked to find upper and lower bounds on zeros of a polynomial function. F of x is equal to 6x cubed minus 11x squared minus 46x minus 24. This is the same as asking us to find an interval that contains all of the solutions of that polynomial equals 0. Well, this is part of a process that we're going to use to find zeros. And that process is always going to start with the rational zeros theorem, which tells us how to write down possible rational zeros. And as you may recall, we need factors of the constant. In this case, the constant is negative 24, and factors of 24 are 1 and 24, 2 and 12, 3 and 8, and 4 and 6. Notice I think of those in pairs. If I'm going to say that 2 is a factor, I might as well write down the other factor, 12. And then our factors of 6, which is the leading coefficient, are of course 1, 2, 3, and 6. Using the rational zeros theorem, I can write down all of the possible rational zeros, and they are listed here. Using factors of 24 and factors of 6, we have 1, 1/2, 1/3, 1/6, 2, 2/3, 3, 3/2, 4, 4/3, 6, 8, 8/3, 12, and 24. Yes, I had to read them. I'm going to put these in order. That is, in numerical order, from small to big in this set. And here's how we can recognize an upper bound. A positive number such that no solution is bigger than it. Well, we're going to find this by synthetic division. The coefficients are 6, negative 11, negative 46, and negative 24. These are in order. We're not missing any exponents. We're good to go. 6 is in the penalty box. How did I pick 6? I know how this ends. As I said, I'm just showing you how to recognize this. For synthetic division, the first 6, the leading coefficient, comes straight down. 6 times 6, 36. Negative 11 plus 36 is 25. 6 times 25, 150. Negative 46 plus 150, 104. 6 times 104, 624. Negative 24 plus 624, 600. Here's the criteria. If the number in the penalty box is positive, and I have no negative numbers in the bottom row of the synthetic division, then 6 is an upper bound. Notice I don't call it the upper bound. It's just that there are no solutions that are bigger than 6. If I state there are no solutions that are bigger than 6, I mean it's also true there are no solutions bigger than 8, or bigger than 12, or bigger than 24. Hope that makes sense. But what this does is, if I'm going to pick from this list numbers to guess and put into synthetic division to find zeros, which by the way means I'm looking for a zero remainder, then I wouldn't guess any of the numbers bigger than 6. So if I have a positive number in the penalty box and no negatives in the bottom row, then that means don't guess anything bigger than 6. It's an upper bound, and just to be clear, we find upper bounds by accident. For a lower bound, we define that to be a negative number. And I'm going to put negative 2 in the penalty box. Why am I choosing negative 2? Again, I know how this movie ends. 6, negative 11, negative 46, negative 24. Synthetic division. It's a good thing we don't have to use long division, isn't it? Bring down that 6. Negative 2 times 6 is negative 12. Negative 11 plus negative 12 is negative 23. Negative 2 times negative 23 is 46. Negative 46 and 46 are 0. 2 times 0, well, negative 2, right? Either way, it's 0. Negative 24 plus 0 is negative 24. If we have a negative number in the penalty box, and the signs in the bottom row of synthetic division alternate, then what we have is a lower bound. At this point, you might cry foul. 0 is neither positive nor negative. 0 can play the role of whatever you need it to have an alternating pattern. So, for instance, a negative and a positive, and then 0 and a positive and a negative. That alternates as far as we're concerned. Negative, positive, negative, 0, negative, that alternates. Negative, positive, 0, negative, positive doesn't alternate, okay? 0 can play whatever role you need it to, but you can't have two of the same thing in a row. To recap, if I have a negative number in the penalty box and signs that alternate in the bottom row of synthetic division, then I have a lower bound. So in this case, we'd say negative 2 is a lower bound, which we again find by accident. Putting these two together, what that means is that all of the solutions to the original polynomial are contained between negative 2 and 6. And so I wouldn't guess any numbers to the left of negative 2. I wouldn't use those in synthetic division. I wouldn't use any numbers to the right of 6. Okay, this original problem was a little bit misleading. It says to find upper and lower bounds. Not something I would really ask you to do. What I would ask you to do is recognize the bounds when you see them. Positive number in the penalty box, no negatives, upper bound, too big. Negative number in the penalty box, alternating signs, lower bound, too small. Use that to guide your guessing, and that's how we can recognize upper and lower bounds. By the way, just in case you're curious, the solutions to the original equation are x equals negative 3/2, x equals negative 2/3, and x equals 4. They're all contained in the interval from negative 2 to 6. Let's look at a completely different way to find bounds. Here we're asked find a number m so that the solutions of same equation, 6x cubed minus 11x squared minus 46x minus 24 equals 0, are contained in the interval negative m to m with square brackets, the closed interval. And there's a note, in this case, m is simply called a bound on zeros. Here's how this one goes. For a polynomial function with a leading coefficient of 1, m is the smaller of, oh my gosh, what is all this? Okay, m is the smaller of the maximum of one of two numbers, either 1 or the absolute values of all the coefficients added together. Notice this stops at a sub n minus 1. It doesn't include the leading coefficient of 1. Or the maximum of the absolute values of all the coefficients plus 1. A little weird, but this is just going to go in the category of it's a tool for your toolbox. So let's see how this is used. And notice that this is a polynomial function, or supposed to be, with a leading coefficient of 1. If I start out with this 6x cubed minus 11x squared minus 46x minus 24 is equal to 0, to get a leading coefficient of 1, I have to divide the entire equation by 6. The result of that is x cubed minus 11/6 x squared minus 23/3 x minus 4. This is getting icky. It has its uses. So we're looking at what's bigger between 1 and all of the coefficients, not including the lead coefficient, absolute values added together. Let's see what we get. So again, the first coefficient, the leading coefficient, we don't bother with. But absolute value of negative 11/6 plus the absolute value of negative 23/3 plus the absolute value of negative 4, that's what's indicated. All these added together give me 77/6. So between that number, 77/6, and 1, which one's bigger? It's 77/6. Okay, but it's supposed to be the smaller of that one or this other number, which is the biggest of the absolute values of the coefficients between negative 11/6, negative 23/3, and negative 4. I think we're looking at negative 23/3. That absolute value, 23/3 plus 1, is 26/3. Let's see what we were looking for. I'm going to scroll back up. The smaller of the results of what we just did, either 77/6 or 26/3. Since 26/3 is 52/6 when we get common denominators, the smaller of those two is 52/6. So m is 26/3. What we've now found is that all of the zeros are contained between negative 26/3 and 26/3. It is a bound on the zeros. I personally like the previous one better. This one is useful too. To recap what we saw before, how do we find an upper bound or a lower bound on zeros? By accident.